past few days, or in the past 3 weeks, we've just been doing geometry. So now I'd like to move on to algebra. I guess this is algebra at least. Give me a minute. Okay. So today's topic is going to be about polynomials and factoring. And basically this is just referring to how we're going to manipulate and handle equations that involve variables to different degrees, as in x that contain terms with like x to the n or something like that, as well as to a certain extent how you can handle polynomials with I think we're going to cover two variables, like x to the n, y, or something like that. Anyway, so I just want to define a polynomial, a single variable polynomial, as an equation of the form of this. This is really just a fancy sigma notation for a sub n x to the n plus, give me a minute, a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus all the way, and then some constant a sub 0 equal to 0. And you've probably seen something like this before in your math classes, although usually they only have going up to n equals to 2 as generally the limit they teach in school. Sometimes they go to 3. But in general, this is the form of a polynomial. And and one special property they have is that every single one of them can be factored as a product of x minus some number. I should use r, but and where these r's are all either complex or real numbers. Well, actually, real numbers are part of the complex numbers. So basically, every polynomial of degree n can be factored into a product of n linear polynomials that are in the form of, actually I forget that there should be leading coefficient in case that it's not monic. But basically, we can always factor this thingy into this. Some constant times n of these x minus a constant, like that. And we call these numbers r1, r2, all the way to rn the roots of this polynomial, as in if we set x equal to any of these numbers, then the equation is going to be true. Right? It's going to equal 0. Sometimes these numbers are also called the zeros. You will see that. Okay, so I think the one tool that computations always use when it comes to polynomials is Vieta's formulas, which revolves around how the roots are related to the coefficients of the polynomial. These coefficients would just be these terms that we multiply by the variable. So Vieta's formula can be generalized for any polynomial of any degree, but quadratic and cubic are the most common ones. We basically have for any quadratic the form of ax squared plus bx plus c equals to 0 that has roots of r1 and r2. Then we have negative b over a. It's going to be equal to r1 plus r2, and c over a equals to r1 times r2. And we actually know this because we can factor the quadratic as a times x minus r1 times x minus r2 from this point right here. So then when we factor and expand this, it's going to be a times x squared minus r1 plus r2 times x plus r1 times r2. So and we can directly just derive that negative b over a is just going to be r1 plus r2, and c over a is just going to be r1 times r2. And this is really how Vieta's formula is derived. You don't actually have to remember this. It can be easily figured out. But yeah, it's not anything that's too complicated. And we'll skip this. And I just put the quadratic formula in here in case in case you haven't learned it yet. It's really just if we're given a polynomial of degree 2 or quadratic, then the roots R1 and R2 are given by this formula. This is actually not actually hard to prove. Ax squared plus bx plus c equals 0. You basically just use completing the square, where you turn this equation into a perfect square, and then you can just take the square root. I'll demonstrate. So first you can divide by a, and then since you want to complete the square, you take this linear term, and then you divide the coefficient by 2, and since you know that the roots have to be equal if it's a perfect square. So you know the roots are going to be something like x minus b over 2a times x minus b over 2a. It's going to be some part of the equation. And then when you multiply it, it's actually going to be x squared minus, plus x squared plus b over ax plus b squared over 4a squared. And basically, we can take this as a constant term, you add this to here, then you subtract it again. So then, let me rewrite this. This game is sort of messy. How should I rewrite this? Okay, reorganize. X squared plus b over ax plus c equals to 0. We know that the roots are going to be, or the roots, since they're not actually roots, but the roots of the square itself is going to be negative b over 2a, and it's going to be a single root since it's a square. So from here, we need to add to this equation the product of these roots, which is just b squared over 4a squared. We have to subtract this since we don't want to change the actual equation. So what we end up with is x squared plus b over ax plus b squared over 4a squared is going to be equal to b squared over 4a squared minus c over a. I forgot the over a here. Right? And this would be x plus b over 2a squared is equal to whatever this thing is. So then you simply just take the square root, and then x plus b over 2a is going to be equal to the square root of this, the square root of whatever this side is. I really am getting this. Actually, it's just going to be b squared minus 4ac all over 4a squared. And this is going to be equal to the square root of b squared minus 4ac all over 2a. So we have x is going to be equal to, oh yeah, I forgot. When we take the square root of something, it's plus or minus the square root here, because positive and negative doesn't matter when you square it. So you have x equals to negative b over 2a plus or minus square root of b squared minus 4ac over 2a. And this just, the denominators are the same, so when you combine it, you'll just get this formula. So that is how you actually prove that this is correct, and because you likely were just given that this is the answer. So yeah, it's not, you don't really need to know it, but it's still nice to know how you can derive the formula by yourself. Anyway, back to where we were. For the cubics, you can check this yourself if you really want to, But if we have the cubic ax cubed plus bx squared plus cx plus d, and the roots are r1, r2, and r3, we have that negative b over a is going to be the sum. C over a, which is this term, is going to be r1 times r2 plus r2 times r3 plus r1 times r3. And then negative d over a is going to be r1 times r2 times r3. So basically, we can apply this to the higher degrees. First coefficient, Alphademic coefficient is a sum, and the constant is the product of the roots. And in general, for degree n polynomial, the coefficient of the term with the product of k of the roots. And this could be sort of confusing, but I'll give an example. Let's say we have a fourth degree equation, x fourth plus bx cubed plus cx squared plus dx plus e. So we know that negative b over a is always going to be the sum of the roots. And we also know that, and then we know that c over a is going to be equal to pairwise, sum of the pairwise products, r1, r2 plus r1, r3 plus r1, r4 plus r2, r3 plus r2, r4 plus r3, r4, like so. Negative d over a is going to be the product of 3 of them, so r1, r2, r3 plus r1, r2, r4 plus r1, r3, r4 plus r2, r3, r4. And then we have e over a is going to be equal to r1, r2, r3, r4. And one thing I forgot to mention here is that notice how the signs of these terms, they're always alternating. So basically, one way to remember this is, you know that this term right here, this second term you could say, which is the sum of the roots, this will always be negative b over a. It will never be anything different, always negative b over a. And from there, for each coefficient after that, you just alternate signs. The next one's going to be positive c over a, next one's going to be negative d over a, and the next one's going to be positive e over a. So that's basically how you remember it. But in general, if you do see a higher degree polynomial and you need these betas, they're really like only concerned with this term and this term, maybe this term, but like generally speaking, it's sort of hard to deal with the middle terms because of just how complicated these expressions can get. So that was betas. I think we'll move on to factorizations, which is somewhat similar to polynomials, but not really. Basically, you can consider factorization of any expression just to be turning it into a product of smaller expressions. And we have that turning the polynomial like this into a product of all of these smaller polynomials. This is the factorization. So yeah, I just want to go over a few common ones, and this one is called Simon's favorite factoring trick for some reason. This one is actually really important, and it might seem sort of clear at first, where it's just y plus ax plus by plus ab equals to x plus b times y plus a. I'll give you an example where it's useful. So we have the problem x and y are positive integers, and we know that 1 over x plus 1 over y equals to 1/6. How many ordered pairs x, y are there? How many ordered pairs of integers, positive integers? Satisfy this equation? I'll actually let you guys work on this for a few minutes, as I want to see if you can figure out how we can relate this problem to Simon's. That's a hint. And you can either message me or if you have like any questions or if you have an answer for some kind of idea. The answer is not 0, by the way. Anyway, so just gonna say that if you guys are just trying, if you guys are just trying to like say, oh, what if x is equal to 1 or what if x equals to 2, you can do like, or you're just like sort of guessing what numbers can work. That'll help you find some of them, but you really can't guarantee that you know all of them. And so like while a method like guessing and checking can be somewhat effective, you'll never really know if when you're done. And so basically Simon's was gonna say this, whenever you see something that's like adding reciprocals of the numbers of variables, you should always look for this. I'll show you why. And especially since, actually I'll go over it later. So how do we go about this problem? First, knowing that we have variables and denominators, you want to clear them. So we can combine this into x plus y over xy equals to 1, 6. So we have that xy is equal to 6x plus 6y, and xy minus 6x minus 6y equals to 0. And does this this looks sort of similar to this, right? Where we have xy and a is -6, b is -6, and we can simply just add 36 to both sides so that we get, let's just do this problem over here. So we know that xy minus 6x minus 6y equals to 0. So then we can add 36 on both sides. So what do we get? You'll find that you get x minus, x minus 6 times y minus 6 equals to 36, right? And generally when we get to this step, all you have to know is that I erased it, but x and y are both positive integers. So all we need to do is figure out how we can multiply two numbers and get 36. So here, all you need to do is list out the possible divisors of 36. So we have this quantity x minus 6 equal to 1, and then this would be 36. This could be 2 and 18, 3, 12, 4, 9, 6, 6, and then vice versa. 6, so. So basically, why can we do this? Well, we're really just taking advantage of the fact that these have to be integers, so we can actually just list out possible values. If we were given that x and y were real numbers or rational numbers, I'm not really sure if this problem would have a finite number of solutions. So this is why we work with integers. So if you know it's positive integers, you don't have to take into account the fact that, or the probability that it's negative. Actually, note that we could actually end up having -6 and -6 here as well. If x and y, actually x and y are positive, it can't matter anyway, and it'll be degenerate. So yes, these are the only possible values we have. And then, so the corresponding ones would just be, here we have 7 and 42, and we'd have 8 and 24, 9 and 18, 10 and 15, and 12 and 12. And since we're counting ordered pairs, we can swap the order of these 4 right here. So we get 4 more. And they specifically be 15, 10, 18, 9, 24, 8, and 42, 7. We can't do anything to this one since they're both the same number. So the answer is actually 9. And you can actually check to see if they add 1/6, and like I show you they do. For example, 1/7 to 1/42 add to 1/6. So this was just a basic example, but generally speaking, if you can somehow find a way to get to Simon's favorite factoring trick, certainly, and you must admit you can. All you have to do is just list out the factors. Once you get to this, like this is a standard step for every problem involved in this. You get to this final factoring step. Like this is just a general method of how to solve problems like that. Yeah. These next few factorizations where we have difference of squares and the sum of cubes and difference of cubes. These are just common factorizations that you might see. They can be easily verified by hand, but I'm not really going to go too far into them. So tips. Often problems will basically they won't say it's a polynomial. They'll just call it a function, like define f of x. You see some like define f of x as some polynomial or something. And yes, functions. And basically, a lot of times they'll either ask you for or give you f of 0 and f of 1. And all you really need to know is that f of 0 is just a constant term, and f of 1 is the sum of the coefficients. This is pretty intuitive as well. Okay, so when you're faced with a cubic or high degree polynomial that you don't know how to factor immediately, you can try out values like -2 to see if there are roots. Basically, you're just trying to guess. It's not really, if it doesn't work, then that's too bad. But if it does, then good for you. This isn't like this isn't a foolproof method, but oftentimes you can get away with cheating a little bit with this. When it comes to quadratics, I think the discriminant of the quadratic formula is a very useful tool. For example, if it has one real root, something like that, a quadratic with one real root. Since it's quadratic, it means that it's a double root, or it has both roots are the same. So you know that this, I don't know why that didn't right. But if it's one real root, the quadratic one real root, it means it's a double root, and the discriminant is 0. And I think, or I just assume you know what I mean by discriminant. This is just the part under the square root of in the quadratic formula, or b squared minus 4ac. So, and we know, if we know that there's no real roots, then the discriminant is just going to be negative. 2 real roots is positive. And if we know that the roots are integers, then we are more coincident. But generally speaking, if you know the roots are integers, you know the discriminant is squared. I mentioned before that Reorganize is useful in equations. Oh, yeah, I did forget to mention that it's funny because you can use Simon's and Reorganize together, because this x, if you let x and y just be the 2 roots, then you have xy is going to be the constant term, and you have this x and the plus y here. So just saying that sometimes you might end up using Simon's favorite factoring trick and read it as together. Another thing I didn't mention is that if a polynomial divides another, all of its roots must also be roots of the other polynomial, and vice versa. So if you have a polynomial with the same roots as another one, then that polynomial must divide the other if it has a smaller degree. And all polynomials will have the same number of roots as same number of complex roots as its degree, which basically just means that if you have this x to the n here, then there are going to be n roots, and that works for literally all n except for 0. And we know that this is just terminology. A monic polynomial is the one with a leading coefficient of 1. So it's going to be, for example, x squared plus 1 is monic, 2x minus 1 is not monic. The leading coefficient is just the coefficient of the term with the largest degree. So I think that's all my notes for this, at least. We can just start with the problems. So with the quadratic equation, this has roots that are twice of this one, and none of them are 0. So what is the value of n over p? First, write down what we know. Note the roots. I feel like the roots of this, the R1 and R2, and then the roots of these be R3 and R4. We have that R1 and R2 are, R1 is going to be 2R. Okay, I should read the problem. We know these roots are twice of those, right? So let's just assume that the roots of this first polynomial is 2R1 and 2R2, and other ones are just R1 and R2. So we might as well just write out what we know about m, n, and p. So we know that m is going to be equal to negative of 2R1 plus 2R2. We know that n is going to be equal to 4 times R1 times R2. We know that p is going to be equal to negative of R1 plus R2. And we also know from here that m is also equal to R1, R2. Right? And we want to know n over p. So how are we going to go about doing this? Well, we have this clear thing right here that says m is, that we have a relation right here. We have m equals to R1, R2, and m equals. So obviously we can just set them equal to each other. So R1, R2 is equal to negative 2 times R1 plus R2. And we want to find n over p. N over p is just 4R1, R2 over negative of R1 plus R2. And from this equation right here, this is just going to be equal to, through substitution, 4 times negative 2 R1 plus R2. This is a fairly simple problem with betas where it's pretty straightforward. They give you information about the roots, and then they want information on the coefficients. So yes, that's all you do. That's it. I think my internet just went out. Give me a minute, or something like that. Who knows? Okay. Did anyone miss anything? Because I really don't know what got through and what didn't. Okay, well, did we at least solve this problem right here? This problem. Well, I'm just going to assume we did, and the answer was 8. Anyway, next problem. A and B be the roots of this equation right here, and suppose that A plus 1 over B and B plus 1 over A are roots of this equation. So we want what is Q, right? So all you need to do is Q is going to be the product of the roots of this equation, which are A plus 1 over B and B plus 1 over A. And if we simply just FOIL it out, it's going to be AB plus 1 plus 1 plus 1 over AB, right? And we also know that since A and B are the roots of the equation here, the AB is going to be equal to 2. So this quantity is just going to be 2 plus 1 plus 1 plus 1/2, which is equal to 9 over 2. So yeah, that's basically that problem as well. Like when you use VADIS, you can solve these problems fairly quickly if that's what the intended thing is. Okay, next one. I'll let you guys read it. The polynomial x cubed minus ax squared plus bx minus 2010 has 3 positive integer roots. What is the smallest possible value of a? So I was gonna ask you, does anyone have any ideas of how to do this problem? You can just private message me suggestions because don't really use them. Difference of cubes is not an option here because there's only one cube. Suggestion. We know that the sum of the roots is a, and that's right because negative a over 1 is equal to the sum of the roots. So we have a equals r1 plus r2 plus r3. And what else do we know? We also know that 2010 is equal to r1 times r2 times r3. And what important information do we know about these roots? That is perhaps yes. Basically, the important thing to notice is that they're positive integers, and this is actually a very restrictive condition. So once you know this, all we have to do is we want to minimize the sum of the roots over the factors of 2010. It's not entirely Diophantine equations are a bit different than this. Anyway, so we can just factor 2010. This is actually going to be 2 times 3 times 5 times 67. So we just want to choose R1, R2, and R3 such that their sum is minimized. So what numbers should we choose for them? And you can just use trial and error, but I think it's quite apparent that one of them should be 67 because it is just so much larger than all of them. And if you multiply it by anything other than 1, you're definitely not going to be minimizing the sum. So 2, 3, and 5, how can we minimize the sum of them? Right? 6 and 5 are going to be our other two numbers. As you can probably see that 6 and 5 added to 11. Other choices are like 10 and 3, 2 and 15. They're all larger than 11. So we can see that this is the smallest possible, the smallest possible value of a is going to be 78. So yes, that just erased. Okay. So I just want to emphasize that even like if you're not even working with polynomials, as long as you see positive integer and then some kind of thing, some kind of thing that you need to divide, just try out a viable solution to such problems. Yes, it's sort of weird. If it is functional, then I don't see too much of a problem. So two numbers CBA, I mean not two numbers, the real numbers CBA form an arithmetic sequence, A greater than equal to B greater than equal to C greater than equal to 0, and the quadratic AX greater than BX plus C has one root. What is this root? So first, in case some of you don't know, arithmetic just means that the difference between the numbers C, B, and A, the difference between B minus C and A minus B are equal. So this means that 2B equals to A plus C, or B equals to A plus C over 2. Yes, that is the right answer. I'm not sure if you've seen these problems where you're just doing it really fast, but good for you. It's actually no way you. Anyway. Or you just did it before with this materials, which is what I wanted people to do. That could have been one too. Anyway, how does this problem work? First, we know that it has exactly one root. And I mentioned earlier, this means that the discriminant is 0. And the discriminant here is going to be b squared minus 4ac equals 0, or b squared equals to 4ac. Right? And we want to find the root. And this root is going to be negative b over 2a, or the square root of c over a. And basically, I got this. I basically got this from Vietas, where b over a, negative b over a is going to be twice of that root, so we divide by 2, and c over a is going to be the square. So you want to find one of these two quantities. And I want to say that let's go for this one, because while this path is doable, square roots are generally a bit more of a hassle than just straight up division here. So what we know is b squared equals 4ac and the ratio of b and a, right? So to do that, we first have to eliminate c from both these equations because it's not relevant. So we have b squared equals 4ac, and we also have 2b equals to a plus c. So we have c equals to 2b minus a, and we can just substitute that into this equation. So that b squared equals to 4a times 2b minus a, or b squared equals to 8ab minus 4a squared, or b squared minus 8ab plus 4a squared equals to 0. And here is actually one of the things I wanted to touch upon. It's one of the problem-solving methods we want to touch upon with polynomials, is that when you want to find the ratio of two variables, you're given something that looks like this, where you have the square, and then the product, and another square, like so, and no constant term. What we can do is we can divide this equation by a squared. So we're just left with this cool thing where it's b over a squared minus 8 times b over a plus 4 equals 0. So we turn this two equation weird polynomial into just a quadratic with b over a as the variable. So in this way, you can actually solve for the ratio without solving for each individual value, which is actually impossible. I mean, it's impossible to solve for each. And we can simply use the quadratic formula on b over a, because that's 8 plus or minus square root of 64 minus 16 all over 2. and say this is 4 plus or minus 2 root 3, I believe. Yeah. Okay. So, but how do we know which one we're taking? Is b over a going to be 4 plus 2 root 3 or 4 minus 2 root 3? And when we come with, or when we have some, you always look back to the problem. We're given that a is greater than or equal to b, right? This means that b over a cannot be more than 1. So our answer, or our value, has to be 4 minus 2 root 3, since 4 plus 2 root 3 is obviously more than 1, and this is less than 1. Okay. Is this our answer? Are we done? Is this it? That was a rhetorical question, I guess. But no, we're not done because we want to find the root, and this is just b over a, and the root is negative b over 2a. All we have to do is multiply negative 1/2 to just get the root. It's just negative 2 plus the root of 3. So yes, that is first. We use the fact that one root where we use discriminant and we use the arithmetic sequence, and after that, use a cool trick to create another quadratic that we can actually solve, and then that's basically it. I do want to mention that going this step, having to like get the square root of 7 plus or minus 4 square root of 3 somewhere along the way. Although it's actually not too hard to realize this is just 2 plus or minus, or this is some kind of 2 plus or minus 2 plus or minus square root 3 squared goes to here. But we don't, then you have an extra condition here, which is sort of hard or not fun to deal with. So generally speaking, this path works. Just want to say that, but I would not recommend it. Anyway, next. How many integers x is the number x to the 4th minus 51 x squared plus 50 negative? So I think the cool thing about quadratics, at least, is that we can substitute anything into them and they'll still be quadratic. As in, if we substitute b over a as a variable, you just use quadratic formula to solve for it, right? So basically, what if you just let y, an integer y, equals to x squared? We have y squared minus 51y plus 50 equals to 0. And you can just factor this as y minus 50 times y minus 1 equals to 0. So we basically want to know how many integers x is this negative. So when is something like this negative? If you think about it, we can divide this number line on 50 and 1, right? If y is greater than 50, then we know that these are both positive and not, and this is going to be positive. But if y is less than 50 and greater than 1, then we have this is positive, but I mean it's not positive, this is negative, and this is positive. So the outcome is negative. I'm going to give y is less than 1, and we're just going to have this is negative and this is also negative. So this outcome is going to be positive as well. So we must have that this y is between 1 and 50, and it cannot equal to 1 or 50 since 0 is not negative. So we simply just have x squared is between 1 and 50, and this means that, okay, I actually want you guys to think about it. We're asking how many integers x are there such that this. So I just want people to like some more answers, please. If you're paying attention. If you're not, then good for you as well. This is on mine anyway. But how many integers are? And this is where you have to be a little bit careful. Okay, stop spamming things. If you are spamming. Anyway. Okay, so I'm seeing a lot of numbers. I don't know who's trolling and who's not, but the answer is actually 12. Now, why is this? You might think that's 6 at first, because we have, it could be 2 squared, 3 squared, and so on to 7 squared, right? But we also have negatives, negative 2 squared, negative 3 squared, all the way to negative 7 squared. As you realize that it says integers and not positive integers. So that is very easy to make a mistake. Be careful when you do these kind of problems. That make sure that you always consider it negative. Yeah. Okay. I think I'm actually done. I think we're done with this problem. So we can go to the next one. If the zeros of this function are integers, what is the sum of the possible values of a? So how can we use this? This is really the only thing we know about the roots. They're integers. Actually, there are multiple things you can do. I'll actually like the method that you really sort of ignore this step first. I actually don't like to use the discriminant method for this problem. Okay, because we can use a cooler thing. We know that R1, if these are the roots R1 and R2, we know they're integers, right? They add to A and they multiply to 2A, right? Am I correct? I probably am. Right. So this is pretty interesting, right? What can we do with these equations? Should I actually do this right? I definitely did. Okay, well basically what happens if we just try, let's see what happens if we try to set them equal. Let's say this is 2y equals to 2 times r1 plus r2, right? So we'd have r1, r2 is going to be equal to 2r1 plus 2r2. And what does this sort of look like? R1, R2 minus 2R1 minus 2R2 equals to 0. Okay, well, this is just Simon's favorite factoring trick, where if we add 4 on both sides, then this left-hand side is going to be, it's just going to be here, and then the right-hand side is just going to be 4, like so. And again, we can use this cool thing that they're integers, right? And we want possible values of a, and we know a is just going to be the a is just going to be out of it's how many different sums and what are they of the solutions r1 and r2 if r1 minus 2 times r2 minus 2 equals to 4. And first note that this is symmetric, so we don't really have to consider the cases where they are just unordered because it's unordered. Anyway, so what numbers can multiply to 4? We have 1, 4, 2, 2, right? We also have negative 1, negative 4, and negative 2, negative 2, because these are integers. There's no restraint on negatives. And note that I did not write 4, 1 or negative 4, negative 1 because we're only looking for the sum. And since this is symmetric, it won't change. It won't be a distinct sum. Anyway. Okay, so we can really just pretty easily solve these. This is just 3, 6, and here would just be 4, 4. This is going to be 1, -2, and this is going to be 0, 0. So the sums are 9, 8, -1, and 0. So when we add all of the a's, these are all values of a, this is just going to be equal to 16. Like so. So this is just going to be your answer. Okay, so we have another problem. This one is actually this is really simple actually. Let A, B, C be 3 distinct one-digit numbers. So again, we know that A, B, C are distinct and they are positive and they're digits. So lots of information. And what is the maximum value of the sum of the roots? So basically, we want to use Viatus because we need the sum of the roots and to find out the coefficient of the x term. So basically, we just expand this first, x squared minus a plus b times x plus ab, then plus x squared minus b plus c x plus bc equals to 0. And notice that we're only like the sum of the roots, so we can just ignore this bc and ab term as it's not relevant. So we just get, although I'm just going to write it because it's not hard to write. You have 2x squared minus a plus 2b plus c x plus ab plus bc equals to 0, right? The sum of the roots here is just going to be a plus 2b plus c over 2. We want to maximize this. And we have a, b, c are the digits of 0 through 9, and they're distinct. We can rewrite this just b plus a plus c over 2. Actually, I think it's actually easy to see when we have it like this. So how will we maximize this sum? For instance, you know that this is all positive, right? We really just want to choose 9, 8, and 7 as a, b, and c in some order, right? And since b is added twice and others are added only once, it makes sense for b to equal to 9. And since a and c, a and 7, doesn't matter what order we add them in, they can be 8 and 7 in any order. So the math is 8 plus 2 times 9 plus 7 over 2. Or this is just 15 plus 18 over 2, 33 over 2, or 16 and a half. So yeah. Like if you notice, a lot of these problems without Viatus are basically impossible to solve. Just interesting. Actually, it's not impossible, but you'd have to do a lot more work. So yeah, just know it makes life easier. My timing is actually sort of good this time. Wow. Okay, this is the last problem before the challenge problem, which is actually I think a bit hard. It's a bit complicated, but let's cover this one. For certain real numbers a, b, and c, the polynomial g of x equals x cubed plus ax squared plus x plus 10 has 3 distinct roots, and each root is also a root of the polynomial of this. What is f of 1? Now, interestingly enough, someone did a false problem before, and I plan to notate off of it. We're looking for f of 1, right? This is the sum of the coefficients, which is actually really not that helpful at all. So really, we want to find what b and c are, and just plug 1 into the equation. So the key information in this problem is that each root of g of x also root of the polynomial f of x. I mentioned before, this means that g of x divides f of x evenly. Okay? So basically, I know I didn't go over this, but you can do this cool thing called long division with polynomials. I just want to use this problem as an example. Long division is pretty interesting. And looks like long division works very similarly to how you would expect normal division to work. So x cubed, right? And you just look at the first two terms, or the first term of each, the quotient, not the quotient, the divisor and the dividend. So x was x cubed, so we know this can be an x term right here. And when x times this whole thing, this whole thing is going to be x to the fourth plus 2x cubed plus x squared plus 10x. And you simply subtract like you do normally. So negative x cubed plus b minus 1 times x squared plus 90x. And then you take the c down to plus c. So then this should obviously be a minus 1 here. Oh, why did I say that was 2? This is a. Imagine. Sometimes I really wonder what I'm doing. Anyway, so this is actually plus a, and that'll change things a little bit. So this is actually gonna be plus a cubed here, so it's just a 1 minus a. So this is just a plus of 1 minus a, like here. Nothing else changes though. So we multiply this, we have 1 minus a times x cubed plus a times 1 minus a x squared plus 1 minus a times x plus 10 times 1 minus a. Since we know that this will divide evenly, as stated from here, we know that this difference right here has to be 0. And what if it's not? Well, first we know that the two leading terms are going to cancel out. So we're going to be left with a term that has a smaller degree than here. And you obviously can't evenly divide this polynomial. You obviously can't evenly divide a smaller degree polynomial by a larger degree polynomial, as a polynomial cannot have a term with negative exponents. So every coefficient here must cancel out when we subtract. And that is a really powerful tool. So all we do is take the coefficients of each of the matching x terms. The b minus a is a times 1 minus a. We have 9b is equal to 1 minus a. We have c is equal to 10 times 1 minus a. Right? So it's actually quite intriguing. So c is just going to be equal to, actually wait, I missed something. Huh, wait, no, I didn't. Okay, I did not miss anything. Okay, so we know that a is negative 89 from here. Oh, where was I? A is equal to negative 89, right? Yes, c is just going to be equal to 900 because 1 minus negative 89 is 90, 90 times 900. And we know that b minus 1 is going to be a times 1 minus a. And that's equal to negative 89 times 90. So this is b equals this plus 1. And let's see, I don't really want to calculate this, but I think someone made calculate before. Negative 8,010 plus 1, which is equal to negative 8,009, I believe. Right, so that's great and all. So we know what a, b, and c are, right? Negative 89, 900, negative 8,009. And all we need to do is find f of 1. So f of 1 cubed plus b times x squared or just plus negative 8,009. It was because everything else is 1, and everything just lagged. So, okay, I didn't get that. What's negative 8,009? So basically just 1 plus 1 minus 8,009 plus 100, and then plus C, and C is plus 900, right? So it's negative 8,009 plus 1,002 gives a negative 7,007, and that is our answer. So yes, that's that. It's actually 2 o'clock already. That's unfortunate. Anyway, I think I'm just gonna give a small hint for the challenge problem, and I'll post the full solution to it later. Okay. So we know that this p of x is a polynomial with integer coefficients such that we have this, right? And what's the smallest possible value of a? And I'll admit that what I said in class is not really going to be all that helpful for this problem. So this is really just how do you know how to use functions, right? So my hint is create another polynomial. Let polynomial r of x define it so that it's just going to be p of x minus a, right? So what is going to be what is the factorization of r of x? And once you know that, and the fact that p of x has integer coefficients, how can we use this and these 2 pieces of information to determine what a must be, what cool things a must satisfy? That's my hint. It's a bit more vague than my previous ones, but yeah, that's it. So good luck on this problem. It's quite difficult. If you solve it, good for you. If not, no worries. And yeah, class is over. You guys can stick around and ask questions if you'd like. But if not, you can leave. Hope you all have a good day.